be a little bit, the way this sentence is phrased is a little bizarre, but as standard free energy change becomes less negative, the equilibrium point continues to move away from completion for the forward reaction. Okay? But while it's phrased really kind of funny, I think it makes sense intuitively. A very favorable reaction that releases a lot of free energy, going in that direction is what wants to happen as fully as possible, right? Whereas something that is, certainly if you have a positive delta G value, then you expect your equilibrium constant to be less than 1, because you certainly are going to, for the forward direction, you're not going to have more products than reactants. If it's a positive delta G, you actually expect things to be the other way, right? And you can kind of get a relative sense of how complete a reaction wants to go based on that magnitude of delta G. So we have equilibrium constant. This is for equilibrium conditions. We wrote it for standard state. Did I write it here? This is essential. Right? The equilibrium constant is related to standard state free energy change. As soon as you're no longer at equilibrium concentrations, you're no longer calculating standard state free energy change. And if you're given a free energy change that says, for the real reaction, for the observed conditions, you're no longer at equilibrium. And instead we're going to define as something called reaction quotient, or capital Q. Okay? Reaction quotient, or Q, describes the observed condition, right? So in real cases, this situation never really happens. Okay? DG is never actually equal to 0. It's going to be non-zero. And so Q, we'll look at it on the next slide, it looks very much like equilibrium constant, but it is for observed conditions, and that's the language you want to look for when you're reading a problem. Like, I did an experiment, I collected these numbers. Those are example of actual observed numbers that you were able to measure. Okay? Or you'll be asked to calculate the free energy change for the reaction, or the reaction free energy change, delta G. So real reactions are very rarely at equilibrium in standard state. So you can get the reaction free energy change, or the change of in free energy for the reaction relative to standard state. So delta G will be equal to the standard state free energy change plus gas constant times temperature times the natural log of reaction quotient, or Q, where Q are your real observable concentrations that you measure in the lab. Okay? Or your experimental concentrations. So it's exactly the same. It's for our simple, just sort of 2 reactant, 2 product, A, B, C, D case. It's concentration of products raised to the stoichiometric coefficient, divided by the concentrations of the reactants raised to their stoichiometric coefficients. But again, this subscript observed, or experimental, or real is on the bottom versus if equilibrium were achieved. So remember that standard state for energy change, or delta G naught, is negative RT, the natural log of KEQ. These are our equilibrium concentrations. So again, observed, actual, real, experimental, any of those words, you're no longer talking about equilibrium. And you can simplify this equation by properties of logs. Pull the RT out into the front, right? Pull our constants out front. And because this would be subtraction, sort of Q minus K, you can simplify this to RT, there's no longer a negative here, Q divided by K. Okay. And we have a name for that Q over K term. It's the mass action ratio. Okay. And what the mass action ratio just tells us is which way a reaction wants to run. These are those directions, and they're based on the sign of delta G. So given this relationship here, if Q over K is greater than 1, okay, this whole term will be greater than 1. Natural log will be a positive value. Delta G will be a positive value. And things will want to run towards the reactants, right? That means the forward direction is no longer favorable. It's a positive delta G. So actually, the reverse reaction is more favorable. Things want to run that direction. Alternatively, if Q over K were less than 1, okay? If this were less than 1, natural log of something less than 1 will be a negative value. We know when delta G is negative, that is the direction of spontaneity. That is the direction we want to go. So things proceed towards the products, towards the right for the direct reaction as it's written. That would be literally all I'd want you to say. It runs towards the products to the right. So here's another even more oversimplified example. Just A becomes B, or it could go back. Okay. So over here we have sort of pure A or pure B, and we're looking at, again, the reaction quotient divided by the equilibrium constant. So our observed concentration of B divided by observed concentration of A. Okay, look at that relative to what you'd expect at equilibrium. Okay. And if this value is less than 1, then we know that we actually want to proceed. We'll have a negative delta G, so the direction of the reaction is trying to go is to the right until it reaches equilibrium. And alternatively, if we have observed values that yield a free energy change that is positive, then we know things are trying to go back towards the reactants until we can reach our minimum free energy. So here is a quick practice problem to do. Okay. Looking at this reaction, it has an equilibrium constant of 2000. During the reaction, the concentration of A, B, and C are as follows. Okay. Calculate Q and decide which direction this reaction is going to proceed. So you, at some moment in time, are able to measure those 3 concentrations of those reactants and products, and then you have to decide, is it still going forward or is it going backwards? What's it going to do from here to try to get to equilibrium?